Alrighty, this is our second and last valence bond theory video. Remember, this is put out by Linus Pauling. We said I had two main things I wanted us to get through in terms of valence bond theory. One was the first video that we did that was making sure that we knew that the hybrid orbitals controlled the electronic geometry of the compound. Okay, so whatever that central atom is, whatever the geometry is what the central atom the hybrid orbitals are, or the hybridization. Okay. What I want us to get into now is to think about multiple bonds and different types of bonds, and we can come at this from uh, a valence bond theory perspective. Okay. So let's look at ethylene. Ethylene looks like this. Remember, we drew this before, and we actually did the um, Vesper theory and said that both of those carbons are trigonal planar because they have three electron groups. Okay. Because they have three electron groups, now we know those carbons are actually hybridized as sp2. Okay. And because they're sp2, they have three identical sp2 orbitals in the trigonal planar around the carbon. There's a p orbital that's above and below. Okay. That's an unhybridized p orbital. So what we get is you can get the overlap of these two, which is right here. Okay. Along the bond axis between the two nuclei. This is what we call a sigma bond. Okay, sigma bond. Sigma means that we have end-on overlap along the bond axis, and sigma bonds are everywhere. Most covalent bonds, well, I shouldn't say that. All covalent bonds are at least a sigma bond. Okay, maybe more, maybe less, not less. At least a sigma bond. I'll shut up. Um, anyway, sigma bonds can be formed from any orbitals. Okay, as long as they're overlapping along the bond axis. Okay, so two s's overlapping, an s and a p, two hybrid orbitals overlapping, a hybrid and an s orbital, two p orbitals overlapping sideways, right? You can get p's and d's, two d's, whatever. As long as they're pointing at each other along the bond axis, you're good, and that's a sigma bond. Okay. Now, the question becomes, we didn't explain one of these bonds in the double bond, right? One of those lines represents the sigma bond that we have. The other one is the other bond. Okay. And if we look at what ethylene looks like at our point right now, we have formed all of our sigmas. There's along these carbons and hydrogens, there's sigmas. There's a sigma connecting these two. And there's two unhybridized p orbitals that are next to each other. And what happens with those is they overlap sideways. Okay. They overlap sideways. So that sideways overlap of two parallel unhybridized p orbitals is the only way you're going to get pi bonds. Okay. So if they overlap along the bond, not along, above and below from a sideways perspective, the pi bond is really above and below the plane. I just made my picture disappear. Above and below the plane of the molecule um, in the thing, right? So here's our trigonal planar two carbons doing their thing. Above it, we have some p or pi bond, and below it, we have some pi bond, right? This is a pi bond, right? This is our key thought right here. You're going to see this over and over again, and I'm going to hopefully drill it into our brains that the only way you're going to get a pi bond is to have sideways overlap of two parallel unhybridized p orbitals. Okay. So remember, sigma bonds can be from anything as long as it's along the bond axis. Pi bonds have to be unhybridized p orbitals that are parallel to each other. Okay. This is the way that it's done. All right. So again, and this is going to hold true. I'm using ethylene as an example, but every sigma bond is the same idea. End-on overlap along the bond axis. Every pi bond is the same idea. Sideways overlap of parallel unhybridized p orbitals. Okay. There's key differences in these bonds because of how they're put together. Okay. One of those is rotation, and sigma bonds can freely rotate. We'll have an experiment all about this semester too. Okay. So if we look at these two dichloroethane molecules, right, they look like they might be different things, but because this bond is end-on overlap along the bond axis, it can freely rotate. And so no matter how it's lined up, those are all the same thing because that bond is actually spinning around. Okay. Pi bonds do not rotate. They can't rotate. Okay. And they can't rotate because the pi bond itself is above and below. For that thing to have to rotate, it would have to break the pi bond and then reform the pi bond. And that doesn't happen unless you force it to do that. Okay. Because the pi bond is above and the pi bond is below. So what it does is it locks these in their conformation. So even though they have the same formula, these two are different compounds. And we saw these same two things when we talked about polar molecules before, right? Because these two chlorines are on the same side. This one is polar. And these two chlorines are on opposite sides. This one's nonpolar because those vectors cancel out. Okay. And they're different molecules, and this happens because that pi bond locks the molecule in place. Okay. All right. So what about triple bonds? Let's use the acetylene as our example here. Um, all right, same kind of idea. Let's think about it through from a, we're going to get our hybrid orbitals first. So each one of these carbons has 2 electron groups. Okay. Because it has 2 electron groups, this dude has to be linear. And because it's linear, that means this carbon is sp hybridized. Being sp hybridized means you have 2 sp orbitals that are 180 degrees away from each other, and it means you have 2 unhybridized p orbitals. So what acetylene does is the 2 carbons overlap end on along the bond axis of their sp orbitals and make a sigma bond. So there's our sigma bond right here. Okay. Now, oh shit, I didn't mean to. Okay. So we now have 2 sets of unhybridized parallel p orbitals. Okay. And each one of those is going to form a pi bond. So one of those, let's get some different colors in here so we can see it. One of those is going to be above and below the plane of the molecule. So that's, say, this one and this one, okay, are above and below the plane of the molecule, right? They're the ones that, you can think about it, they're the ones in the plane of the screen, right? They're going this way and they're overlapping this way and they're making a pi bond. I don't know why I clapped. Okay. Um, the other red. Okay. The other one is in the plane of the floor or the desk or whatever you want to think about. It's in the horizontal plane, and right, and it's this p orbital, which goes front and back, overlapping with this p orbital, which goes front and back. And so it has some pi bond in the front and some pi bond in the back. So here's our pi bond in the front, and here's our pi bond in the back. Okay. And so really what happens is I think of triple bonds as like a corn dog. Okay. And it makes me hungry, but I love corn dogs. So anyway, you've got a tube of sigma bond running through the middle, and then you've got the crusty cornbread of the pi bonds wrapped around the outside. And so there's a lot of electrons in here, but they all know where they're supposed to be. And there's a sigma bond in the middle, and then there's pi bonds around the outside. Okay. When we're thinking about bonds, we're going to have to be able to know what we're talking about in terms of counting things. Okay, I call this a key skill. We're going to count sigma and pi bonds in a Lewis structure. And this is how we're going to figure it out. Because if you're looking at a Lewis structure, you can see if something's a single bond, a triple bond, or a double bond. And from there, we can know how many sigma bonds and pi bonds are there. Okay, let's think about it from the bond order. Single bond has a bond order of 1. Double bond has a bond order of 2, and triple bond has a bond order of 3. Okay. So we said this, I said this, I shouldn't say we, I said this at the beginning of this dude when we said sigma bonds. Every covalent bond is at least one sigma bond. One, one, one. You can only have one sigma bond. Okay. A single bond has no pi bonds. Remember, the double bond had one sigma bond and one pi bond, and the triple bond had 2 pi bonds. Now, notice what's happening here. Our bond order is equal to the number of pi bonds and the number of sigma bonds added together. So 1 equals 1 plus 0, 2 equals 1 plus 1, 3 equals 1 plus 2. So you can always figure these out. Okay? And the reason I want you to be able to figure these out is because we need to look at some crazy business like this and count how many sigma bonds or pi bonds are in here. Okay? I'm going to show us how to do it. All right, first thing I do is even though sigma bonds are listed first, it's easier on your brain to count the pi bonds first. Okay, I circle them all, whatever. You're going to be able to draw on the paper, so do whatever you want to do. 1, 2, 3, 4, 5. Every double bond has 1 pi bond. There's 5 double bonds, so that's 5 bonds. Okay, every bond, not just the pi bonds, but every bond has a sigma. So now count everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so there's 18 sigma bonds, 5 pi bonds. Okay, that's how we can figure it out. This compound is cool. It's called cinnamaldehyde. It smells like cinnamon. It smells really good. Anyway, they should say now do it, not no do it. So I'm sorry that I'm stupid. Okay. All right. This is what I expect you to be able to do with valence bond theory. We've already talked about hybrid orbitals and how we can link hybrid orbitals to the geometry. You need to be able to pick those out. Okay. You need to be able to tell the difference between a pi bond and a sigma bond and explain how they happen, right? When you talk about pi bonds not rotating, right? So you have isomers that are locked in place. Sorry, excuse me. And we want to be able to count sigma bonds and pi bonds in a Lewis structure. This is going to be super helpful when you get to organic to be able to do all of these things. Plus, it's going to be on a test coming up for you guys anyway. So learn how to do it. Let me know if you have any questions. Um, I'm here, and hopefully I didn't make it too terribly horrible. I'll catch you later.